Let's think a little bit about the different clues that have led us to conclude that we have these lithospheric plates moving relative to each other. Now, the first clue, and this is something that I think many students, even in elementary school, first experience when they first learn about geography, is it looks like the continents could kind of fit into each other. And the most obvious one of these is when you look at this kind of little pointy part of South America. And if you have a more detailed map, it really is amazing how well it seems to fit into into the Nigerian basin right here in Africa. It looks like at one time this little pointy part was nudged into this part of Africa, that they were actually connected. And if you're a little bit more creative, there are other parts of the world that you can kind of start to see how they might have fit in with each other in the past. And that, that by itself, that's just a very small clue, but it kind of hints at, well, maybe if they at one time were next to each other, or if this was kind of connected, then they've had to moved apart at some time. Although it doesn't tell us that it's still moving or what might have caused the movement. And it definitely doesn't definitively tell us that they even moved. Maybe this is just a coincidence that this coast of South America looks very similar to this coast right here of Africa. Now, the next clues, which really came over, I would say, about the last 60 or 70 years. The first clue is that, okay, if you go to the mid-Atlantic ridge right here, so if you look at the Atlantic Ocean, let me look at this photograph right over here. So it's a little, you don't normally see the oceans highlighted like this, so let me make it very clear to you. This right here is South America. This is South America. This right here is Africa. This right here is North America. And so if you actually look at the elevations in the middle of the ocean, people noticed in the middle of the 20th century that, gee, there's a ridge in the middle of the Atlantic Ocean. There's kind of a mountain range that goes straight up the middle of the Atlantic Ocean. So that by itself doesn't tell you that you have these plates that are moving apart, but it is kind of a curious thing to look at. And not only is there's a ridge, there's a lot of underwater volcanic activity. You have magma flowing out and lava flowing into the water, and it's kind of forming this ridge that really goes across the whole Atlantic Ocean. There are other ridges in the world like that, underwater ridges. You have one over here in the Pacific Ocean. You have these here in the Indian Ocean. So that by itself, that's just a little clue, but that by itself doesn't tell you that these plates are actually moving apart at the ridge. The more conclusive, this is just the beginning of the clue, but what made this conclusive is, one, the separate discovery, and this is what's interesting, is that you have these separate discoveries in different domains that eventually let you kind of come to a pretty neat conclusion. So you've had a separate discovery that if you look at different eras of magnetic rock, or maybe I should say different magnetic rock from different periods in geologic time, and you can tell where they are in geologic time by how they're layered. So this would be newer rock, this would be newer, and then this would be a little bit older, and then this would be even older. Geologists noticed something interesting. If I were to take magnetic rock, and if it was molten lava, and if it were to harden, remember it's magnetic rock, so it would want to align with the poles the same way a compass would. So if I had a bunch of magnetic, so let's say this is some lava right here, and so the molecules can align themselves. Since when it's liquid and they can align themselves, they're going to naturally want to align with the poles. So they'll naturally all want to align in one direction. They'll naturally all want to align in one direction because of Earth's magnetic field. And so when that lava hardens into actual rock, that alignment will kind of be frozen. Now, if Earth's magnetic field was constant over time, then when you look at magnetic rocks from any period, you would expect them all to be aligned in the same direction. So since we're taking a cross section of rock here, let's say an alignment towards the North Pole looks like this. And what I draw it like that, that's kind of an arrow pointing into our screen. And let's say an alignment pointing to the South Pole would look like this. This would be an arrow pointing out of our screen. So what you would expect is the newer rock, that kind of the alignment, the alignment of the rock would go into the screen. And then the older rock, it would still go older into the screen. So if I were to draw a top view, let me draw it like this, just so I make sure that everyone is on the same page. So let me just draw a cross section like this, so we know what we're talking about. Let me draw a cross section like this. And so this is the surface up here. This up here is the surface. When I talk about going into the page, so when I talk about into the page, that means that the magnetic rock would be aligned in that direction. And when I talk about going out of the page, it means, so if I were to draw it like that, that means that the magnetic rock would be aligned in that direction. Now, like I said, if the magnetic field of Earth never changed, then lava that essentially turns into hard, cools down into non-lava rock, or you can say freezes into rock, it would all point into the same direction regardless of when it hardened. Regardless of when it hardened. This would be the situation in a constant magnetic field. But what we've seen is that that's not the case. When you look at older magnetic rock, and depending on how old you go, you have the newer rock that's aligned with our current magnetic field. You go a little bit older, and right now we think it's about 780,000 years ago, roughly. You have to find rock of that age, magnetic rock that hardened at that time. It's actually in the opposite direction. So it's actually, the magnetic rock has hardened in a way so that it's pointing, it's as if the North Pole was at the South Pole now, the magnetic North Pole. So it's aligned in the opposite direction. So it's kind of pointing out of the page here. And then if you get even older rock, it's more aligned with our traditional direction. So it's more aligned than that. And so the only reasonable conclusion that we can draw from this is that Earth's magnetic field has actually fluctuated over time. So magnetic field fluctuates. Magnetic field fluctuates. Now you're probably thinking, Sal, how is this relevant to plate tectonics? Well, once you accept that magnetic fields fluctuate over the history of the Earth, there's another interesting observation you can make about the rock that's kind of at the basin of the ocean floor. So not only do you have at the middle, this mid-Atlantic ridge, do you have these volcanoes spewing kind of new rock into the ocean, creating this kind of underwater mountain ridge. But it also turns out that the rock that forms the sea floor also contains a lot of magnetite, which is magnetic. And what's really interesting about that, so let me draw. So let's say that this is, so we have a top view just like we have over here. So let's say that this is the mid-Atlantic ridge right here. So mid-Atlantic ridge. Now this is really cool. So when they look at rocks that are very close to the mid-Atlantic ridge, they're aligned, and once again we're looking at rocks at the floor of the ocean, they're aligned in a way that you would expect with the current magnetic field. They're aligned just like that, the way that you would expect when you're looking at the magnetic rock that's close to the ridge. That's close to the ridge. But if you go a little bit further, and when I say a little bit, I'm talking about thousands of miles. But when you go further out from that, you have stripes of other magnetic rock that is going in the opposite direction. When it's going in the opposite direction, it's going like this. It's going like this. And what's even cooler than the idea that it's switched directions depending on how far you've gone from the rift is that there's a symmetric stripe of magnetic rock on exactly the same distance, or roughly the same distance away from the rift, that's also pointing in that same direction. That's also pointing in that same direction. And you go a little bit further out, and you'll find some rock that's pointing in the original direction. And even better, you go on the symmetric other side of the actual ridge, and you find another set of rocks that's doing the exact same thing. So if you accept that Earth's magnetic field has kind of been flip-flopping over time, the only reasonable conclusion, at least that I could think of, or that the geologists can think of, is that sure, all of this was formed at a similar period in time. This came out as lava, magnetic lava, and then it all aligned with Earth's magnetic field, and that's why it looks similar. You fast forward in time some, You fast forward in time some, and the only way, or actually let's not fast forward in time, the only way that these could have formed, and they could have been so similar, so if we rewind in time, the only way that these purple magnetic rocks could have aligned this way in exactly the same way, at exactly the same distance, if at some point they were much closer to each other, if they were actually connected. So if we rewind in time, maybe at the mid-Atlantic rift, you had all of the purple rock. You had all of the purple rock coming out from those underwater volcanoes. And at that time, Earth's magnetic field was the opposite as it is right now. And then, of course, you had this blue rock. You had the blue rock that is looking like that. And so this seems like a reasonable explanation. This rock and this rock were at some point touching. They were actually formed at the exact place and at the same time. And so if this is the case, if at one point this purple rock was all together and they formed at the same time at the mid-Atlantic rift, we're assuming all the rock was, well, we don't have to make that assumption, but if you assume that they formed at the same time and that based on the pattern it really does look like they do, and it's a symmetric distance away from that rift, then the only reasonable conclusion I can think of is that the rift has had to move apart. The rift has had to move apart from this period to that period. And there was a time when all this blue rock was together. So that by itself, that frankly is the most definitive evidence in the 1960s where it kind of became conclusive that you did have these plates that were moving away from each other. You did have these plates that were moving away from each other. And obviously, if the plates are moving away from each other at some point, and that means that, just based on the way the map looks, at some points they're also going to be moving into each other. We could talk more about that in future videos. But, right, at certain points they're actually moving on. One plate is moving under another. And we'll talk about how that might partially explain, or we'll talk about all of the explanations for why we think that plates might actually be moving. But now if we fast forward to more present times, now that we have GPS satellites and all the rest, we can actually measure the movement of the plates. This is actually an image from NASA showing the vector of the movements at different points on the surface of the planet. And you can see we've gotten a lot of vectors from the United States, so it's hard to read since it's so chock full of vectors. But you can see right over here in Hawaii, the Pacific plate at that point is moving in this northwest direction, as measured by GPS satellites. And I want to make clear, this movement is relatively slow. It's roughly the speed at which fingernails grow. But if you do it over millions of years, that actually amounts to thousands of miles. So we're talking on the order of about a centimeter a year for most of the plates. Some of the plates might be moving a little bit faster, maybe close to 10 or 15 centimeters. But most are moving about a centimeter a year at the same rate your fingernails are going. But this is fascinating because we can actually measure it because GPS is so accurate. Over here, it looks like the North American plate is kind of rotating generally in that direction. We have, the Nazca plate right here is moving roughly in that direction, moving into the South American plate. I'll leave you there right now. And actually, before I leave you there, this is another thing that I got off of Wikipedia that shows that same magnetic striping. It's maybe a slightly neater drawing. I don't know which one might be more helpful for you. But I'll leave you there in this video. In the next video, we'll think about some of the theories. We know now that the plates are moving. Let's think about some of the theories as to why they might actually be moving.